pleasure to welcome Professor Otmar Hilliges, who's going to join us remotely. Otmar is currently an associate professor of computer science at ETH Zurich, where he leads the AIT lab, and he also serves as the head of Institute for Intelligent Interactive Systems. His research is in machine perception of human activity, computer vision, and machine learning. Specifically, he's interested in spatio-temporal understanding of how humans move within and interact with the physical world. He researches algorithms, methods, and representations for human and interaction-centric understanding of our world, from videos, from images, and other sensor data. He's interested in many different application domains and has a long-term passion for augmented reality, which I hope he will share with us here today, and mixed reality as well, and has been involved in mixed reality research since the beginning of his career. Prior to joining ETH, he was a researcher at Microsoft Research in Cambridge. He has published more than 100 peer-reviewed papers in the major venues on computer vision, HCI, and computer graphics. 20-plus patents have been filed in his name on a variety of subjects, from surface reconstruction to AR, VR. Amongst other sources of funding, Otmar Hilliges is a recipient of the prestigious ERC grant, Starting Grant. Today, Otmar's presentation is Where Are You Going? Mixed Reality. Thank you. Otmar, over to you.
Hello, hi everybody, and first of all, of course, apologies that I can't be with you in person. I wish I could have. Previous engagement here at ETH right after prevents that from happening. So yeah, before I start sharing my excitement about mixed reality, I'm going to show you some maybe not quite state-of-the-art mixed reality in order to establish a little bit of street cred. So what you're seeing in the next video here, in this video here, is an actual augmented reality system circa 2003, so 18 years old almost. For some reason, the application domain that we picked was herding of virtual sheep. Please don't ask me why, I don't remember. But that's sometimes the case in academia. But it has quite a few interesting elements, right? There's an interaction between virtual objects and real objects, in this case, spatially tracked brethren of these animals here. And we'll see a few other aspects. First of all, the display here is projected into the real world, and then we bring other elements, what today you would call a mobile phone, into the system, and virtual objects migrate from one display to another display. There's even natural language interaction, right? So this person kind of issues speech commands, and then new sheep are spawned in that virtual world, and God forbid, actually, let's call it removed, right? And then this here is what you've actually been waiting for. This is kind of a 3D view or a perspective view of the 3D world, where we see now one of these animals being moved around in the 3D world. And last but not least, and this is very fitting with the session today, a user wearing a head-mounted display that kind of picks these poor little sheep up and then dunks them in virtual color buckets. And fortunately, they're being let go at the end. So by now, you may not be super impressed when you see that, right? You're used to slightly different frame rates, better visuals, and so forth. And you know, in hindsight, of course, I agree. Back then, I was excited about this. But a very smart advisor, Gudrun Klinker, who's over in Munich, already then said the reality of augmented reality can be rather disappointing. And you know, there's a harder truth underneath this, and that truth is that augmented reality is a very hard problem, right? And that's also why I showed you this video of this imperfect mixed reality system. And the question then is, why is it so hard, right? So first of all, it is hard because you have to get everything right. You have to have a display of high brightness, good transparency, so you can see the real world. You have to have an almost perfect localization and mapping system. So some of the hardest computer vision problems need to be solved. On top of just knowing where the scene is or where the world is in terms of geometry, you also need to understand semantically what is going on. And then last but not least, once you have a system that can reason about the 3D world with a high level of fidelity, you still need to answer the question, how does it reason about my own actions in that world? Right, let's fast forward a little bit. Roughly 10 years ago, I was fortunate enough to be part of an excellent team that kind of explored how we can use our hands and how we can reason about our hands in interaction with virtual objects, and a system that allows you to, in real time, reconstruct the world around you and capture to some level of granularity the interaction between humans and that world. And these made for much cooler, much more impressive demos than herding virtual sheep. But other than allowing us to record cool videos, it did something deeper down, right? And what it did, at least to me, and quite a few other people, was it gave you a feeling of augmented reality being possible, right? It being something that you could make real. And it had quite a bit of academic impact, but it also was instrumental in actually launching what is now known as HoloLens. So the internal incubation effort was based on these two demos. So I think this feeling of augmented reality could be a thing was mutual back then. So let's go back to Gudrun's earlier statement of, augmented reality, the reality can be a little bit disappointing. Another pioneer of augmented reality, Steve Feiner from Columbia University, pre-2010 once told me that really it just needs a big financial muscle to make it happen. And so now in 2021, we're really putting this to the test, because there's not only one big financial muscle, but there's lots of them pushing lots of these problems. And so if we arrive in the present day, we can hand-wavily claim that the display question has been solved. At least there's lots of commercial efforts out there now. Computer vision, in terms of reconstructing the 3D world, has also made a lot of progress. So here's basically a computer's view of the Louvre Museum in Paris. And it's not only that we can reconstruct the 3D geometry, we can also start to understand the semantics of the world. So I'm claiming all of these problems have been solved. So the question then is, what is not solved yet? And I have to say that for me, the question is of how does the computer know what I want, right? How I am interacting with the world and with other people. And so I'm going to do a worldwide tour of our own research in this space. Some of it is connected to what Siu talked about a little bit earlier. Some of it is quite different. So the first question that we need to solve in this setting is, of course, the computer or the headset that you're wearing needs to have an idea of the state that the human is in, that is myself, and that there's other people out in the world. So problems like pose estimation, but also hand pose estimation. What do I point to? What objects do I touch? And eye gaze estimation. So where do I look at in the world? These are all important research questions. In general, all of them are a really wicked problem, right? So they fall in the class of inverse problems, where we typically have a high parametric model. I illustrate this here with a 3D body model that we need to fit to low-dimensional sensor data, so images, for example. And this is a demonstration of what a recent algorithm does. Because it has to fit a high parametric model, it can get stuck in what we call in engineering bad local minima. So it does find a solution that aligns the hands and the feet here, but clearly you as a human can tell that that is a very bad solution. And so this is the underlying hardness of that problem. Of course, Siu has shown you some of the work that addresses this, and there's a large community that's working on it. Here's one of our contribution. We're really excited about the algorithmics components of this problem, where we really combine traditional numerical optimization and deep learning, where a neural network basically predicts for each of the parameters of my high-dimensional model, how should I progress as I fit this model to the 2D data to avoid such bad local minima. And so here's a comparison. This went rather quickly. On the right-hand side, ours has already found a good solution, where the previous state of the art is still searching and may not actually always find a good solution. But it's not only numerical optimization that is outperformed, also state-of-the-art direct regression methods turn out to be less accurate because we can exploit this iterative fitting. So this, you don't need to understand everything that I said, but what you can take away from this is that we're beginning to get to a state where the computer can understand where humans are and fairly accurately understand what they are doing if I see them in front of me. So the next question then becomes, if I want to have maybe a conversation with a virtual human, right? So think of telepresence right now. Wouldn't it be great if I could appear in 3D on the stage and maybe even attend the coffee break and have a chat with you? And for this, now there's a lot of work on generative modeling. Again, I'm going to be very quick about one particular paper that we're going to publish this year in a couple of weeks, actually, where we're combining traditional computer graphics methods that give us very accurate 3D geometry, which is important in the setting of augmented reality or virtual reality, where you actually want to see people from different viewpoints. And we combine this with the power of recent progress in deep generative modeling. So you probably have heard of the whole deepfake debate, and this roughly falls into that direction. What's exciting to me about this work is that this kind of gives us a disentangled control over various aspects. So in this video on the right, you see how the identity of the person that we're rendering changes, but the facial expressions and the head pose, so where the person is looking, stays exactly the same. And then if we start changing the other parameters over here, such as the head pose, for example, or the expression, we keep the identity and the appearance consistent over those, which again would be super important if you want to build a mixed reality telepresence system. So those are kind of the the underlying building blocks that where academia and also industry research in general is making or chipping away. So we're getting really to a state where we can think of these always on displays, maybe wearing an augmented reality headset all day long. And then one thing comes into play where we actually have to think about what is the type of content that we're showing and how are we showing it without overloading people, right? So this is the promise, again, a toy example, but we're looking around in the real world and we're seeing information that's potentially useful overlaid directly in 3D, right? So here, basically, we're labeling toys, but there's lots of other toys, and we're only labeling those that we're interested in. So that's the promise of having information everywhere, having it everywhere and in any moment that you need it. However, this is kind of the nightmare version of this, right? Where you're completely overloaded with information. You do have information everywhere, but not necessarily the kind that you want. So in recent work, one of my PhD students has come up with a technique that addresses this issue by learning how to only show information that is both spatially and semantically relevant. So consider yourself being in a supermarket and only being interested in the price of, let's say, alcoholic drinks. First of all, given the view direction into the world, we only want to show information that's actually perceivable, right? So something that is in our field of vision. And then we only want to show that information that's actually semantically relevant for the task right now. If you're shopping for alcoholic drinks, you don't need to see the labels for anything else. And so this is a decision problem, right? A policy that an artificial agent can learn. And we believe that learning cooperative policies is a very exciting direction of research. So here's a result of such an agent that has learned from gaze patterns. So the green dots are the fixations of an actual user, which information is useful, and it only shows it when when the user is actually looking somewhere close by. And so this is something where I believe if you have a real augmented reality system that can kind of understand what your task is and show you only the information that's relevant to you at this moment in time, we're beginning to get into a state where something like this would actually excite almost everyone. And so I believe there's a lot of technically very, very challenging problems, but also really exciting applications if we get these kind of technologies right, such that they can display the right the right content for the right context and adapt that towards or depending on the situation that we're in right now. Obviously, knowing what I want to do and having to know what my task is all the time also raises some privacy and security concerns. And these are open questions, and I hope you guys will have lots of fun in the panel discussing these afterwards. And so with that, I would like to close and thank you all, and I hope that next time I can be there in person. Thanks, everyone.